So V is equal to some linear combination of vectors v1, v2 through vn. Then T of V is also equal to a linear combination. It's a linear combination of the transformation of C1 times T of V1 plus C2 times T of V2 plus Cn times T of Vn. So essentially I can take the transformation of each one of those particular vectors and then multiply them by their scalars, and that would be the transformation of the vector V. And this one's a really nice property because it helps us, especially if V1, V2 through Vn is a basis set. So for example, I have this example that I have right below that on this PowerPoint. I have let T go from R2 to R2, so it's a linear operator, with R2 to R2. T of 2, 0 is equal to 3, 6. And I know that T of 0, negative 15, yeah, T of 0, negative 15 is equal to negative 12, negative 9, 27. Okay. I can't read my own handwriting sometimes. And I want to find T of 4, 5. Now I want you guys to notice that they don't tell you what the transformation is. We have no idea what the transformation is. Only thing we know is what the transformation does to two of my vectors. I know that the transformation takes my vector 2, 0 and converts it to 3, 6. I know that my transformation takes 0, negative 15 and converts it to negative 9 and 27, right? And with just that limited information and the property 2, I can figure out what's the transformation of T for 4, 5. Because if you look at it, 2, 0, and 0, negative 15, these guys are basis vectors for R2, right? These two vectors, 2, 0, and 0, negative 15, are vectors that I can use to be able to span all of R2, right? These guys are linearly independent vectors. So what I'm going to do is first thing I'm going to do is I'm going to say, okay, let me see if I can write 4, 5 in terms of 2, 0, and 0, negative 15. So let me put that on board. Let's write. I think I can erase this now. Write 4, 5 in terms of 2, 0 and 0, negative 15. Right? Essentially, I need to find the linear combination of those two vectors that would get me 4, 5. I mean, we've done this type of thing so many times. It's not even funny anymore, right? When you think about it. I can create a augmented matrix to figure this out. But this was fairly easy, I think. If I multiply a by 2, I get 4, right? And if I multiply negative 15 by negative 1 over 3, I think, then I will get 5. So I think A is equal to 2, B is equal to negative 1 over 3. Okay. But if you wanted to, you could do an augmented matrix. I think I'm fine without doing that. So I know that if I wanted to, I could write this. I could say 4, 5 is equal to 2 times 2, 0 minus 1/3, 0, negative 15. Okay. And guess what? Now that I have it written like this, I'm going to just do a transformation, right? I'm going to do a transformation. So let's do a transformation on this. So I have t of 4, 5 has to be equal to 2 times t of 2, 0 minus 1/3 t of 0, negative 15. Okay, that's what property number 2 says right here. Okay, what is t of 2, 0? Well, t of 2, 0, we said that was 3, 6, right? What's t of 0, negative 15? Well, we said that was negative 9, 27, if I wrote that correctly. That gives me, I don't know, that's 6 and 12. This is plus 3 and negative 9. I think so. So I get, what's that, 9, 3. Again, if I made any mistakes, you guys will be able to catch it and see it and make sure I did it correctly. But I think it's probably right. Okay. So that's 9, 3. And let's do one more. This one not with a vector, but with a polynomial, because I wanted you guys to see that. Again, it helps us when we start talking about vector spaces later on. Okay. All right, guys, let's do it. And if I'm speeding along, please pause the video, go back and listen to it again. Without you guys here, there's nobody to tell me to slow down, go slower. So I just kind of go, hopefully at a speed that you guys still can understand what I'm saying, understand what I'm doing. And then the last thing here, before I go to the next part with matrix transformations, is I say let T be a transformation from P2 to P2. If you forget what P2 is, this is polynomials of degree 2 or less. Be a linear operator. With, I'm going to have that T of 1 is equal to 3x squared minus 4. Bless you. T of x is equal to 2x plus 3. And T of x squared is equal to 7x squared minus 1. And I want to find the image of 2x squared plus 4x minus 3 under t. Now, image is just a fancy word of saying what the function value is. So image is essentially what you get when when t, your function, is applied to 2x squared plus 4x minus 3. So essentially what we're saying is I just want to find what is t of 2x squared plus 4x minus 3. Just a fancy way of saying that. What is it equal to? Well, again, just like we dealt with before, this 1x and x squared form a basis for P2, if you guys remember that when we did our basics section. 1x and x squared form a basis for P2. So with those, right, it's easy for me to figure out how to write this guy, 2x squared plus 4x minus 3. I can write that as 2 times 1, right? plus 4 times x plus, oh, so that should be negative 3 times 1. Negative 3 times 1 plus 4 times x plus 2 times x squared. I mean, it's kind of obvious, right? But I can. I mean, it could have been a little bit more difficult terms, coefficients, but in this case, it's fairly easy. And now I want to find out what is t of 2x squared plus 4x minus 3. Well, it's going to be negative 3 times t of 1 plus 4 times t of x plus 2 times t of x squared. 2 times t of x squared. And let's just plug it in, plug it in. So I get negative 3 times t of 1. T of 1 is 3x squared minus 4. Plus 4 times t of x. T of x is 2x plus 3. Plus 2 times t of x squared. T of x squared is 7x squared minus 1. Okay. And then I just have to be careful. This is going to be 9x squared plus 12. This is 8x, I think, plus 12. Okay. So far, so good. Plus 14x squared minus 2. And let me get all my terms together. I think that's going to be 5x squared plus 8x. And then I have 24 minus 2 plus 22. If I did that correctly. Okay. And that is right. Again, this is a linear operator, right? I think we did both examples of linear operators. Linear operator from R2 to R2, and this is a linear operator from P2 to P2. That's what we have. Very, very good. It doesn't have to be a linear operator, but it makes it a lot easier if it is a linear operator you're going from when you do these types of transformations. All right. Very, very, very good. Okay, so let's talk about, with our remaining time, let's talk about matrix transformations. Okay, let's see, where's my eraser? Matrix transformation. All right. All right. Let's just write down the definition, shall we? Definition. A linear transformation that can be written in the form T of V equal to A times V, where A is a n by n matrix and V is a n by 1 vector, or n by 1 matrix. It's a column vector. It's called a matrix transformation. Call it matrix transformation. Right? So a linear transformation that can be written essentially as a matrix. So if a linear transformation can be written as a matrix times a vector, then it's a matrix transformation. This is essentially what it is. So if I can write any if I could write that linear transformation as a matrix times a vector, and that's it, nothing else added, then it is a matrix transformation. So here are some examples of matrix transformations. Okay, I have two of them on here. I think these are enough for what we want to do. Here's the first one. I have y1 equals 3x1 plus x4. y2 is equal to 7x2 plus 5x3. And y3 is equal to 4x1, yeah, plus 3x2 minus 8x3. So the way you want to think about this is that the y values are my output, right? And the x1, x2, x3, and x4 are my inputs into my function. So if I want to write this as a matrix equation, okay, I'm going to write it this way. I'm going to say T, and I'm going to replace y1, y2, and y3 with T of x1, x2, x3. T of x1, T, it doesn't, it's T of x1, x2, x3, and what is it? We go up to x4 then? Right, those are my inputs. Right, and I'm going to get 3 rows for my output, right? Right, y1 is going to be equal to 3x1 plus x4. y2 is equal to 7x2 plus 5x3. And y3 is equal to 4x1 plus 3x2 minus 8x3. Okay. This is what we've already dealt with before. I just wanted to show you guys that, okay, this is going to be how my T is. So this is T of my input, x1, x2, x3, right? I have output, which is going to be 3 rows. 1, 2, 3. 1, 2, 3. y1, y2, y3. Okay? y1, y2, y3. Now let's write this in terms of let's write this in terms of a matrix equation. This becomes T of x1, x2, x3, x4 equals. I'm going to write this as a matrix equation. So if I have a coefficient matrix, I think it's going to be 3, 0, 0, 1, right? Then I have, what is that, 0, 7, 5, 0, I believe. And then the last one I have is 4, 3, and negative 8. 0. And then I have my matrix x1, x2, x3, x4. Now can you guys see the matrix equation, right? T of V, V being x1, x2, x3, x4. This is going to be A, right, which is a size 3 by 4, okay? And then here's my V, which is a size 4 by 1. Okay. So I'm able to write this as a matrix equation. So T of V is equal to A times V. One more. one more 2. I have t bracket xyz is equal to, here I have 3x plus 2z, 6y minus x, 8z. Right, so if you haven't been noticing, if you haven't been looking at the PowerPoints, right, then it's not written exactly like this. If you look at the PowerPoint, it looks like this. It's t of x, y, z is equal to 3x plus 2z, 6y minus x, and 8z, right? And if you guys have noticed, this is just the same form that you will see at a vector function having this similar form, right? So you take it, you put it in a vector, and it outputs a vector, right? You've seen this in Calculus 3, if you've already taken Calculus 3. But I like it in this form. It's a little bit easier to see how this is going to be a vector, right? So how this is going to be the matrix form of this, and how this is a vector, right? So let's see here. So we have t of xyz, which is going to be my v. xyz is my v. It's equal to, I'm going to write my matrix here. I have 3, 0, 2, 0, they try to get me. Dr. Wesley, -1, 6, 0, 0, 0, 8 times xyz. Again, this is t of b equal to a, which is a 3 by 3, times b, which I know to be a 3 by 1. All right, so those are matrix transformations. And what is not a matrix transformation? I have one example of that. I mean, there's multiple examples of something that's not a matrix transformation.